What are the advantages of letter-based tokenization that we use in machine learning models? It turns out there's quite a few advantages. This is a question that we got from TikTok asking about the attention mechanism when we are looking at tokenization of our letters. Our input data is organic data like language that needs to be converted into numbers, and that number can be represented as a lookup dictionary. You can do this in terms of words, sentences, full sentences, even paragraphs. You can tokenize from that perspective. Though letter-based tokenization, there's actually some advantages there. Let's take a quick look at some of our advantages of letter-based tokenization. We've got a finer granularity, which captures more details from the text, right? That's going to be important from an individual character's basis. We can handle rare words easily, such as words that we might not have defined even, which is pretty powerful. So breaking down all our words, all our inputs into letter-by-letter input tokens, that's going to be a far more advantage. Compact vocabulary is another aspect to it. It's a lot smaller, usually just the alphabet letters, right? A through Z, digits 0 through 9, and punctuation. And we can capture that very easily compared to word-based tokens. That it's going to give us a really small output layer size, right? So, maybe to 50 to 60 units rather than 10,000 or 100,000 units, which is going to take a lot more compute power to train, and also you're kind of sticking yourself into a fixed dictionary. We also have the ability to capture structures of words and more complex words with words related to their structure. We can actually capture some of that nuance that we get from a letter-based token, and we can't get that so much with just a simple word-based token. We also have a consistent input size, which makes input for the models when we're capturing the words of varying lengths. It breaks down into characters so that it's, as opposed to one word being, one token or one value, you could have a word like the word character is a lot of words versus the word of is only a couple letters here. So lot amount of letters, a small amount of letters. We're actually going to see some of that variance captured in that form. We also get better generalization, right? With letter-based token, this enhances our ability to models to generalize across different but similar words with patterns at the character level, and that applies to multiple words, which is kind of neat. We also have noise robustness, improves the noise against typos, right? So spelling's a common problem, and with letter-based, character-based tokenization, we will be able to capture the meaning of misspelled words or words with intentions or slang words, right? Those kinds of things will be able to be captured there as well. And now this also works well for any of these other kinds of models that we might run into: RNNs, LSTMs, CNNs, transformers. It works well for CNNs because you usually have channels with a CNN. So if you have like a word token of 10,000 letters or 10,000 tokens, right, where you would have to represent a bunch of filters with 10,000 output, that would just explode the CNN. It would make it nearly impossible. So in order to use the CNN with a large number of output sequences and tokens, you'll want to do that with letter-based tokens. So overall, with letter-based tokenization, you get more granular and potentially more robust ways to handle the text in machine learning models. It can find details and misspellings. It's more forgiving. It's really powerful. Also, it's a lot easier than having to capture a large number of words in a dictionary. Potentially, you'll have wasted space as well, where you have infrequently used words, right? Where they're just reserved for those tokens, and guess what? Those words may show up once or twice. It's just not going to be that beneficial unless you have tons of data. And so actually the text letter by letter, character by character tokenization is going to be better even for large or small data set sizes. So we have a follow-on question here from TikTok that asks us, what are, if any, current models, machine learning models, that take advantage of letter-based tokenization? With letter-based tokenization, it gives us a lot more control, power, speed, and performance. And there are specifically models that are built for this because of the advantages that we get with letter-based tokenization. Now you might say, hey, do large machine learning models like the LLMs, these large language models, do they use letter-based tokenization? Now they use a combination of that. We'll probably jump into that a little bit more, but let's take a look at the existing models that are out there in the wild that give us the capability to leverage immediately without us having to make our own. right? What are the current models that use letter-based tokenization? And they're all going to be roughly the same, but here in this case, so we've got some more original, well-known, so it's a 2015 classification char convolutional neural network here. We also have the RNN char, so it just tokenizes it and puts it through, CNN filters, RNNs. We have a deep emoji model where it's all emoticon based. Oh, this is kind of interesting. All right, so we can, I guess, decode what the meaning is for a sequence of emojis. That's kind of neat. We also have Elmo, which is common. Elmo embeddings represents character-based bidirectional LSTM. LSTM's a little previous generation technology, right? We use transformers now these days. GPT-3, which is a mainstream model, right? This is probably one of the main questions, like, are there any existing models that leverage byte level encoding or character level encoding? In this case, yeah, they call it byte level. So it can capture the tokenizations on a byte by byte basis. Now, obviously, you have letters in English A to Z. Other languages, it goes beyond that, right? So you've got more characters or less characters. You might want to represent mixed languages, and so you can continue to grow from there. And byte pair encoding is going to combine models. So this is not byte pair encoding. This is it's like it, but it's just letter by letter encoding, right? So it's more sequential. We have OMFIT here, universal language model for fine tuning is another model here, a little newer, 2018. We also have fast text, which came out of Facebook for the fair. It is creates word embeddings from character level engrams. Oh wow! So I would more call this like a more hybrid model. And from that perspective, and then you also have character BERT with bidirectional encoder representations from transformers. This is going to use character level encoding with a convolutional neural network. Wow. And word piece tokenization. So this is another one. It does use some word-based or letter-based tokenization, but they mix in other strategies as well. And then we have Charformer, which is a more advanced character level tokenization built with a I think it was transformer. Yeah, it was. All right, so this is the newer one. So if you want to see the newest model that's available, check out Charformer, and that will be a model that you can use for character level tokenization. Are there other kinds of tokenizations compared to letter tokenization, where we take all the letters in the sentence sequence and convert each letter into a token? Are there other strategies that we can use? And the answer is yes, there are. There are a lot of other strategies. There's a ton of strategies. You can take any combination of all those words, tokens, byte pair encoding, word level, sentence level, paragraph level, partials. You can do a whole bunch of things. You can even use Diffie-Hellman strategy, where you find the most repetitive sequence of words, right? And then convert that into a token. So there's a lot of things. It's kind of like a compression approach, where it takes you can do a lot. There's just a ton. And so if we kind of jump down here to see a variety of types of tokenizations that we have at our fingertips, what are the advantages between each? So you get word-based token, where it's going to split all the words that are inputted into the sequence. Now the problem is you might have a lot of misspellings. So certain words that are meant to be one thing but are another will have different meanings, but they really are intended to be the same. You might have problems with that. So that'd be some the disadvantage. And then, yeah, misspellings is a disadvantage, right? Also, large vocabulary size, so it's going to be more expensive, a lot more expensive to train from that perspective. Then we have sub-word tokenization, which means, it's not the full word, but it is partial derivatives of the word. So byte pair encoding, where we take two characters or 2 bytes, we find the most common sequences, right? This is kind of a compression approach, where we take the highest frequency of bytes and then convert those into a single token. So for example, I don't know, let's see here. So ER is a very frequent kind of byte pair, right? So that would be one potentially. Let's see here. So AN is another one. I like this one. So AN, we see a lot of ANs out there. Just trying to see. So we've got another AN here, for example. Those ANs would be converted into a single token, for example. So that's one approach. We've got word piece, which probably slices words by certain amounts and deals with, it's similar to byte pair encoding, just bigger chunks, right? And we have unigram language model, considers all possible tokenizations by selecting the best one. This is kind of like a compression model, like gzip style, Diffie-Hellman, where we're going to be capturing the most frequent character sequences, and then we're going to capture those as tokens. And we also have sentence-based tokenization, which is pretty big, right? We take entire sentences and tokenize the entire sentence. That's kind of crazy, but you can use that for things like sentiment analysis, and it's going to be very fast and efficient. But not suitable for finer grain or large language models. It's going to be classification, right? You'd only want to do that for classification. You get n-gram, which is pretty straightforward. It's just going to take a fixed sequence of characters. And so like if you have a word, like the word captures, you're going to say the n-gram will be it'll be 3. So every 3 characters. So CAP is 1. TUR is another, and then ES is the last 2 there. So that would be n-gram tokenization. Is just a more consistent approach. It's going to be smaller. It does have data sparsity, but at the same time, it's like higher complexity in terms of computation compared to letter by letter tokenization. So it's kind of like a middle ground, but it is a strategy that actually quite a few existing LLMs take advantage of. You can do syllable tokenization. No one really does this, not a whole lot. But if you are working forward to build some sort of specific meaning around language related to syllables, this would be an interesting pattern for you, because where it's interesting for syllable structure is important based on your model. Whatever your output's going to be, you can tokenize using syllable tokenization. Morphographical tokenization splits words into their components like stem words. Oh, okay. Right. So we remove suffixes, right? So like running would turn into run, right? And so we could, this is a strategy that's used for indexing traditional words in a word index engine. This for searching. You take the words that are typed into a search, and then it takes the stems and the roots of those words and creates indexes based on those, so that way you can capture meaning from that perspective. So this is a strategy used in search engines, but it's not. It could work. It could work fine. Depends on your use case. Captures meaning of structures in where. So like English, for example, would work really well here, where you don't really need the ing right at the end, where it doesn't have a whole bunch of real intent behind what that word is. We've got a few left here. Tokenization by part of speech. What? Hold on. Split or tags based on grammatical parts. Oh. Interesting. So noun, verb, adjective. This has a significant advantage, specifically when you're working on grammar. Maybe you're building a spell correction. Maybe, well, actually more of a grammar correction system, right? So you can capture intent and grammar and structure around languages, and then you can find and highlight any misspellings or misgrammar written, useful for tax or crime or grammatical context. Interesting. Grammatical context. And the last one here, very final one, hybrid approach, where we combine all these strategies. You can actually combine any of these strategies together. So you would have, what do the large language models do? They typically do full dictionaries based on all languages in the world. So we combine that, right? That's like tens of thousands or hundred thousands of words in a dictionary. And then you have byte pair encoding beyond that to capture misspellings and other infrequently used words. And then you have letter-based token as the very, very end, at the end where nothing else can match. So you do the full spectrum of all these strategies together. And this gives you the capability to have the most advanced model. And this is what the large language models, they do. They take advantage of all the tokenization strategies. Now, if you're building a general purpose large language model, that's actually probably a good idea. However, all the other kinds of models, you want to pick one.